All right, so we're looking at optimization and linear programming. So the thing about optimization is whenever you have a system of linear inequalities that produces some kind of bounded region, and you have another function that's related to what makes that bounded region true, then the maximum or minimum value for that related function will always occur at one of the vertices of the region. It's never just going to be some random point in the middle that creates that maximum value. It's always going to be one of your corner points. There is a problem here worked out as a good example. Not a bad idea to look at it. But I'm going to go ahead and skip down here and start working this problem. So question number 1, the first thing you need to do is graph your inequalities. The first one is just y is greater than or equal to 2. That's a pretty simple one. Here's 2. I have a horizontal line. I know that for my inequality symbol that I'm going to shade this above, but again, I'm not going to do that until later so that I don't crowd up my paper. The next equation is actually 2 equations stuck into one. That says x is between 1 and 5. So those are vertical lines. I'm going to draw one at 1. I'm going to draw one at 5. And I know that this means that my solution is going to be in between those 2 lines. The last equation is y is less than or equal to x plus 3. I started at a positive 3 and go up 1 over 1. Now I usually recommend that you draw as many dots as possible on your graph. That way you can try to be sure that your graph is a little more precise. When I connect these dots, I'm going to look at my bounded region. Again, I know I'm above the blue, between the pink, and below the black line. So I'm looking at this area right here. Okay. They've given you a 4th equation here. This is your maximization, or the equation that you're looking to maximize or minimize. Usually this can be like some kind of cost or a profit equation or something like that. But for this case, we don't know what this equation stands for, but we're still looking to maximize it. So the first thing I want to do is identify the x and y values that create those vertices. So I have my first point is right here. That's the point 1, 2. I also have the point 1, 4. And the point 5, 2. And the point 5, 7. Not true. 8. This is 7. From there, I'm going to plug these x and y values into this other equation to figure out which one gives me the maximum and minimum. So when I plug this in, 3 times 1 minus 2 times 2, that's 3 minus 4, negative 1. 3 times 1 minus 2 times 4. 3 minus 8, that's a negative 5. 3 times 5 minus 2 times 2. 8 minus, no, not true. 15 minus 4 is 11. 3 times 5 minus 2 times 8. 15 minus 16 is a negative 1. So looking at these 4 numbers, the maximum occurs whenever you end up with an 11 at the point 5, 2. The minimum, a negative 5, at the point 1, 4. Let's just work one more of these. Question number 2. I'm going to start with, again, y is greater than or equal to a negative 2 this time. So here's negative 2. My next equation, y is greater than or equal to 2x minus 4. Starts at a negative 4, goes up 2 over 1. The last equation I'm going to have to do a little bit of work on. First thing I'm going to do is subtract the x to the other side. When I divide this by a negative 2, remember you're going to have to flip your inequality signs. That's a positive 1/2 x plus 1/2. Now, this has a y-intercept of 1/2, so technically you can start here at a positive 1/2 and go up 1 and over 2. I like to be a little more precise than this, though, and I want to start at a good corner point. So I say if my y-intercept is a fractional number, maybe my x-intercept would be okay. Remember, to find your x-intercept, you're going to plug in a 0 for the y. If I plug a 0 in for y, either here or here, doesn't matter which one, I'm going to solve this. I think it's easier over here. When you plug in a 0, the y term goes away. That gives me x equals a -1. So -1 is my x-intercept. From there, I can count my slope of 1/2. Up 1 over 2, up 1 over 2. If you notice, it did go through that 1/2 point that I originally graphed, so it would have been okay, but I think it's more precise to use a real point. Again, if I was going to shade this, above the blue, above the pink, below the black, I'm looking at this area right here. 3 vertices again. First one is right here. That's the point -1, 2, 3, 4, 5, -2. I have 1, -2. And 1, 2, 3, 2. I'm going to plug these points into a different equation than last time, but I'm still looking for which one gives me the maximum and which one gives me the minimum. If I do 4 times -5 minus a -2, that's a -20 plus 2, -18. If I do 4 times 1 minus a -2, that's 4 plus 2 is 6. If I do 4 times 3 minus 2, 12 minus 2 is 10. The maximum value occurs here at 10. The minimum value at -18. I'm not going to work this next question for you, but I will write down what your vertices are. If you would like to go ahead and work this question out, you do end up with the corners at 0, 2, 4, 3. And the last one, you're going to have to solve using substitution or elimination because you get a fractional answer. Feel free to finish working this question out if you'd like.